Hey guys, welcome back. We're continuing on with AC power single phase, and I just showed you this crazy drawing of all the different waveforms and all how the power acts all weird, and depending on the different kind of circuit that we've got here. And so we're going to actually continue to talk about power. And in AC there's actually three different kinds of power, guys. Unfortunately for you guys, I mean, in level 1 life was easy, and everything was a resistor. And there was only one kind of power, and you guys learned that power is the voltage times the current in the circuit. And unfortunately, in alternating current, it's not that simple, okay? It's much more complicated, and you can't just take the voltage and the current and multiply them together and get the power. There are actually three kinds of power in AC, and we're going to talk about them one at a time here. I've written some notes out for you here. I hope you can see them. If you want to pause your video and take these notes, you should do that. But I'm just going to talk about them because I've already pre-written them here, okay? So, three types of power in AC. The first one we're going to talk about is what's known as true power. And true power in the circuit is any power in the circuit due to the resistance of the circuit, okay? So, true power is any power in the circuit due to resistors in the circuit, okay? And your kilowatt hour meter reads true power and true power only. And it is the power in the circuit that does work. Meaning this, if I've got this circuit here and this is a resistor, this is all going to be true power, and it is going to be doing a bunch of work because this 10 amps and this 120 volts is going to cause this resistor to heat up. And work from level 1 is, either you're moving something or you're trying to heat something up. Those are kind of the two very broad definitions of what work is, okay? So it is power in the circuit that's doing work. In this case, it would be heating up. Maybe I could use it to boil water or something like that. That is the power that you were dealing with in level 1 because everything was a resistor and it is measured in watts. The symbol is P. And the formulas you probably are familiar with. The power in the circuit is the voltage times the current, but not the voltage times the current. It is the voltage dropping across the resistive part of the circuit times the current through the resistive part of the circuit, okay? And in level 1, everything was a resistor, so you didn't have to worry about these little R's. But there were two other formulas that you learned in level 1. P is equal to I squared R. Well, in level 2, power is the current dropping across going through the resistor squared times, the value of resistance in ohms, I squared R. The third formula that you learned in level 1 for power, E squared over R, that formula still works, but now it is ER squared over R. The voltage dropping across the resistive portion of the circuit squared divided by the value of the resistor, okay? So that is the first type of power that we have in an AC circuit, and it is all to do with the resistive part of the circuit. But we know now that there are other components in a circuit, and so what about them? Well, the other two components that you could have in a circuit are inductors and capacitors, and they cause reactive power. And so the note here says power in the circuit due to the inductors and or capacitors of the circuit. And a kilowatt hour meter ignores reactive power. If you look at this thing right here, I have a big inductor here. Here you can see the kilowatt hour meter moving back and forth. It's not actually turning. It's moving backwards and then forwards and then backwards and then forwards. And all day long that happens. Causes no true power, okay, even though it's drawing a bunch of current. It doesn't do any work either. I mean, that inductor there will not heat up. It'll be just sitting there, using some power and returning it. There's no heat involved. If it is heating up, it's because it's actually an RL series circuit, because I've got students who've said to me before, listen, I'm going to put a giant inductor in my heating duct. It's going to draw 100 amps all day long. It's going to be doing this all day long. My meter's never going to move, and I'm going to heat my whole house up with it. Well, you can't do that because this thing is storing energy. It is not using energy like this thing does. Same with a capacitor. Doesn't heat up, okay? It just stores energy and returns it. That's what's going on with this. And you won't be able to use it to heat your house. And if you are heating your house with it, it's because it's one of these. It's an RL series circuit, and it's the resistive part of the thing that might be heating up. And if it is, you're paying for it. Okay, because, yeah. So it doesn't do any work. It's measured in volt-amp reactive VARs. Okay, so, it's due to capacitive reactance and inductive reactance, which is why it's called reactive power. Okay, guys, so if that helps you to remember, volt-amp is reactive there. Its symbol is also VARs in a formula, and the formulas are here. Now, the VARs, or the reactive power in the circuit, is going to be the voltage dropping across. This says EX and IX, but it could be EXL times IXL if it's an inductor, EXC times IXC if it's a capacitor, or maybe just EX times IX if there's both in the circuit. Okay, so these formulas, guys, are the same ones you learned in level 1, except for it's for reactive power. Power is equal to E times I. Reactive power is voltage dropping across the inductor times the current through the inductor or capacitor or whatever. Same with this one. Power is equal to E squared over R. Oh, sorry. Power is equal to I squared R times R. Okay, now it's IX. It's the current through the inductor or capacitor squared times, XL or XC, depending on which one it is. Power is equal to E squared over R. Now it's reactive power is the voltage dropping across the inductor or capacitor squared divided by the ohms value of the capacitor or inductor. So that could be EXL. EXC could be XL, XC. All right. And, this is not going to make that much sense, but once we start applying these rules, hopefully it will make more sense. Okay. So just bear with me as we go through these. Then we'll actually try to, apply it to a circuit. Okay, guys. Okay. So the third type of power in AC is called apparent power. And the apparent power is the phasor sum of all the powers in the circuit. And the other two powers are reactive power and true power, guys. So the apparent power is going to be basically the phasor sum of the true power and the reactive power in the circuit. It is measured in volt amps, shortened VA. Its symbol is also VA. And have a look at the formulas here, guys. The VA, power is equal to E times I. VA, E total times I total. All right. The VA, I squared R, I total squared times, the total resistance. Okay. Z. VA is E squared over R, E total squared over Z. Total voltage across the circuit divided by the impedance of the circuit. Total voltage squared divided by the impedance. So these are all like the whole circuit values, guys. These ones here were just the reactive power values. These ones here were just the resistive values in the circuit. All right, guys? Now, we need to talk about power phasors for a minute, because the phasor sum of all the powers in the circuit, what do the power phasors look like? And so here are some power phasors. Now, I've drawn the two power phasors that we're dealing with and then the sum of the two. Now, this one here is true power, and it's on the horizontal line, guys, because it's the resistor. It's due to the resistance of the circuit. Resistors are always on the bottom. They're in phase, okay, guys? And inductors and capacitors, they cause the current to lead or lag by 90 degrees, so it's sitting here on the vertical side. The reactive power will always sit on the vertical side. The true power will always sit on the horizontal side. Always, always, always. And the VA will be the sum of the two. Okay, and it'll always make a nice right angle triangle here, with that one being the sum of the two. Phasor sum of the two. Just ignore this for a second, because we need to talk about one more thing. All right, guys, we'll come back to this. The last thing I want to talk about is what's known as the power factor. And electricians and electrical engineers are always talking about the power factor of a circuit, because it's a nice, easy way to, describe a circuit, and, so that we know exactly, how it's behaving and how much of its power is true power and how much power is reactive power, etc. So the power factor, guys, is going to be the ratio of the true power to the apparent power in the circuit. And it always will be a number between 0 and 1, but it also can be expressed in a percentage. So if you had a power factor of 0.6, you could also say that that was a power factor of 60%. Okay, so you'll see it either way. And there's two formulas for calculating power factor. The first one is, basically exactly this. It's the ratio of the true power to the apparent power. So if you want to figure out the power factor of a circuit, it is going to be the true power divided by the apparent power in the circuit. And the reason it's always a number between 0 and 1 is because you will never have a circuit that has more true power than reactive power, or than apparent power, right? Because the true power is going to be this adjacent side, and the VA, or the apparent power, is going to be the hypotenuse, and you're never going to get a hypotenuse that's shorter than the true power. You could have one that's equal, because if there's no capacitors or no inductors, or there's no VARs, you could have a situation where there's only true power and the VA is equal to the true power. That would happen in a resistive circuit, and there's other times that could happen. But in that case, the power factor would be 1 or 100%. Okay, guys? So you're going to have a number between 0 and 1 if you've done this correctly. And if you get a number over 1, you've done it incorrectly. By the way, a power factor of 1 means that the power and the VA are equal, and that's also known as unity. Okay, so if you hear the word unity, or you see it in your homework, unity power factor, it means that the power factor is 1, and the power and the true power and the apparent power are the same. It also means that the phase angle is 0 in the circuit. Right, guys? Now, this one right here, this one right here. Another formula for power factor is the power factor is going to be the cosine of the angle. And if you want to know why that's true, then you need to look at the power phasor diagram. Like, what we're going to do here is look at this. This is K, okay? Just trig. K is the cosine of the angle, is the adjacent over the hypotenuse. Now, we know that the power factor is the power over the VA, and the power is always going to be the adjacent, and the VA is always going to be the hypotenuse. So, since the cosine of the angle is equal to the adjacent over hypotenuse, and the power factor is equal to the adjacent over the hypotenuse, it is fair to say that the power factor is equal to the cosine of the angle, okay? Because you're basically going, this is equal to this is this, so this is equal to this, okay? So this is equal to that, if that makes sense, okay? And I understand, guys, that none of this makes sense, and that's normal. It's not supposed to make sense. It's totally complicated right now, but once we apply it to a circuit or two, hopefully it will start to make more sense than I've just made this right now. All right, guys? So in the next video, we will look at a circuit, and we'll see if we can calculate the true power, the reactive power, and the VA in the circuit, and the power factor in the circuit. Okay, guys? So stick around for the next video.